So last day we looked at cosmic potential energy. We said we can't use MGH because G changes. I did some calculus speak, and Kedra and Dustin, what you want to write in the box is that one there. Negative PE equals negative big G, big M, little m over R. We're going to talk more about why it's negative today, but we said the reason it's negative, well, there was a calculus reason that I gave to my calculus students, because if you take the derivative of that with respect to R, you get the force equation. But it's also negative because we defined zero energy to be out at infinity. We said if you were on the edge of the universe and we let you go, you won't fall because there's no gravity acting on you. If you won't fall, you must have zero potential energy. But to get there, you would have to do work. You would have to add energy. So you would have to start with less energy to get to zero. What numbers are less than zero? Negatives. We did one question where we used conservation of energy, and we said, unfortunately, it's just a lot of writing. In fact, today we will be doing almost the longest question of the year. There's only one that's longer, and I'll show you how we'll try and cut corners, but I'm sorry, it's rocket science. Did you think it was going to be simple? No. But first, pause for a second. I have a lovely little sim right here. It's from a website called PhET. And so this is doing a planet around a star simulation. And notice that although we ignore it, you can see typically the object that's being orbited also has a bit of a wobble. There is going to be a bit, we ignore that. This is highly exaggerated. The Earth does not make the sun wobble that much. But I like the fact that it kind of points that out. And then there is your lovely circular orbit.
Sorry for the interruption.
Continuing on. Reset. We can also simulate a star, a planet, and a moon. So this little green or cyan moon is going to go around the Earth. I'd like you, and I mean this, try and imagine what path you think that moon will draw out as it orbits the Earth. If you had a big camera, Kedra, above the solar system and were staring down at the solar system, or if you were floating in a spacesuit looking down, and we sped things up, what path would you see the moon tracing out? Imagine it. And it's prettier than you can imagine. The moon traces out that path in green. That's what you get when an object is revolving around a circle, around another object that's revolving around a circle around the sun. The ancient astronomers, when they were graphing these, they loved to talk about the music of the spheres or the cosmic dance. And you can kind of see why, if you were carefully graphing stuff like this out, you would get a delighted smile on your face as you realize, oh, there's some beauty up there. We can also have a sun, a planet, and a comet. So here's our stable planet, here's our comet in an elliptical orbit, but it's been slightly deflected by the planet just then as it went by, and so its orbit is changing ever so slightly. And in fact, most comets don't have a stable orbit. In fact, we don't see most of the comets in our solar system because they've long since crashed into the sun. The sun is a big cosmic vacuum cleaner in our solar system, as is Jupiter, which is good. Otherwise, we would have a lot more impacts on the Earth. Okay. You'll notice this comet made an elliptical orbit. We have been looking for years and years for some kind of comet or other celestial object to come around the sun and form a hyperbola, a hyperbolic orbit. And we found our first one just last year. That is our first ever interstellar object. If objects come around the sun in an ellipse, that means they're from our solar system, probably from the Oort cloud way out there. But if objects come around the sun in a hyperbola, that means they're not from our solar system. Our sun just happened to capture them with its gravitational field, but they started way out there. We found our first interstellar object last year, and we spotted another one this year. So you're the second group I've been able to say that to. Luke Skywalker grew up legendarily on a binary star planet, Tatooine. So we can model that mathematically. So here is a stable orbit with a planet and two binary stars. This would be a little bit interesting because, for example, right now there would be no nighttime on this planet because you've got a star on either side. And right now, there would be 2 stars in the same section of sky. It would be crazy hot. So we don't know exactly how if life could evolve or what it would be like. We have Trojan asteroids. In between Mars and Jupiter, we have the asteroid belt. It looks like a want-to-be planet that couldn't, I guess, manage to pull itself together with a strong enough gravitational field to become a clump, but it's there. How many of you have seen the Star Wars scenes where they fly through the asteroid belts, dodging asteroids? That's complete BS, complete garbage. NASA sends their satellites through the asteroid belt of our solar system all the time. The asteroid belt is so empty, the debris is so far apart that the chance of collision is so close to zero, NASA doesn't even bother factoring it into their calculations. They don't care. So this whole dodging through an asteroid belt is yet another thing that Star Wars has totally butchered. That's not going to happen. Space is just bigger than you can imagine. You could have a very crowded asteroid belt, lots of debris, but it's so big, you'd still have thousands of kilometers between every single object and have plenty of room to spare. This is one we can model mathematically, 4 stars in a stable orbit. We can model it. We've never spotted one because if I reset it, if you make a slight change to the initial conditions, not only is it not stable, things go pretty haywire pretty quick. So you'd have to have a really fluky situation for that system to start up out there. Although, if you found 4 stars in a perfect, lovely ballet, that might be evidence for a super intelligent, super advanced technology race that was able to move those stars that way. If you watch this little green one here, this is our satellite. It's going to do what we call a slingshot. It's going to pick up speed when it goes past the sun and when it goes past this planet. So it picked up some speed there twice, and it picked up some speed from that purple object. NASA tries to do this whenever possible. Really what's happening is we're gaining some kinetic energy from that planet. Technically, that planet is losing some kinetic energy. Technically, it's slowing down. Kinetic energy is a half mv squared. That planet has a big enough mass that even though it's losing some v, it's not. You can calculate it. It's hardly measurable. But the satellite has a small enough m, it's going to gain a lot of v. We do this all the time. Some of the NASA orbits and some of the European Space Agency orbits, if you look at their probes, they're almost mathematical works of art. They'll be slingshotting around 4 or 5 planets. They'll be going around the Earth once or twice, around Venus once or twice. It's really quite well done because it's not free energy, but it's close to free energy. The planets aren't going to miss it, at least not for a few billion years. You can do a double slingshot. So again, watch this little green satellite here, and it gets a slingshot around the sun, around the purple planet, and around the cyan planet. That happened really, really quick, so you watch again. So actually there's kind of 3 speed boosts going on here, 2 slingshots from a planet, but also a slingshot from the sun. Here is an example of a hyperbolic orbit. So this, if we spotted an orbit like this, we would say, ooh, it's interstellar. It's from out of our solar system. We spotted our first one last year. It was an object, you may have read about it in the news. They gave it, I think, a name in Hawaiian. So it started with the letter O, and it had a bunch of M's and A's and U's and H's and was about yay long. I can't remember how to say it, but we confirmed that was an interstellar object. Planets actually orbit in ellipses, not circles. However, they orbit in ellipses much closer to this purple one than to this green one. This purple one, when you look at it with the naked eye, does it look like an ellipse or does it look like a circle to your naked eye? Yeah, the reason astronomers didn't know that planets orbited in ellipses is because, in fact, one time as a math activity, we graphed Earth's orbit around the sun. You can't tell it's not a circle by looking at it. It looks like a circle. But if you crunch the numbers really carefully, oh, this horizontal axis is slightly different from the vertical axis, and so I guess it's not a perfect circle. The astronomers just initially figured it was a flaw in their data, that they weren't measuring accurately, and that's why, because they assumed it would be circles. It wasn't until Kepler, who was just before Newton, came along, who said, I think ellipses models things better. Now, as you go further and further out, Pluto's orbit is much more akin to this green one. In fact, Pluto's orbit is so elliptical that for a stretch it ducks inside of Neptune, which is one of the reasons why we eliminated Pluto as a planet. Get over it. Here's 4 planets, not 4 stars. 4 planets in a stable orbit, a double-double. Again, it's highly unlikely, although we can model it mathematically, it's highly unlikely that you would see that in nature because a slight change to the initial conditions and things get pretty chaotic pretty quickly. Although it's kind of looking like good stuff is happening here. If I kind of advance, ooh, no, you saw a big crash. Those 2 planets collided. Debris would be now scattering everywhere, crashing into the other planets. Not good. But those are just some stuff you can do with orbits. It's a fun little sim to play with. So pause here. Show solar system app. Done. Record lesson. I am. I like example 2. I like example 2. I like example 2. There's a small problem, Robert. Can you all look up? Not only do I like example 2, I like example 2, I like example 2. Turns out I also like example 2, I like example 2, I like example 2. Maybe make that a 3, but I like that one as well. Kiefer, can you read me the first 3 words of this question? How much what? This is asking us to find work. Now you're going to go on your formula sheet to the work energy section. Kiefer, what's my equation for work? Don't write this down. Why can't I go that? Because it would be nice. Why can't I do that? Do you remember? This equation had a condition, and you may want even, you can write this on your blue sheet if you want. Only works for a constant force. As we move away from the planet, is gravity a constant force? You have another equation for work, a more complicated one. This is why I said the math is going to be ugly, but a far more useful one. What's the other equation for work? That one doesn't have any conditions on it. You can use it. The other thing I want you all to notice, read this question. Did I say the word orbit anywhere? So we cannot say, gravity is what's pulling me in a circle. I don't have that option. If I'm missing something, I can't use that. Okay. What word did I underline, Kiefer? Here's what we're imagining. We want to put a satellite at that height. We'd like to figure out how much work, how much energy, how much rocket fuel to get it to the right height. So we're going to, in this situation, because we're lifting, assume we start at rest, lift it up, and end at rest. What's my change in kinetic energy then? What was my initial speed? 0. What was my final speed? 0. So what's my change in kinetic energy? Now the problem with this, Kiefer, look up for a second, is if we let it go, the satellite's going to come crashing back down to the ground. That worked far worse than I planned. Note yourself, Mr. Do It. Don't use the brain. Use the tennis ball because it bounces a bit more normally. The problem with this is if I let it go, it'll come crashing back down. To put it to a stable orbit, I'll also have to give it kinetic energy. How much kinetic energy? A half mv orb squared. We'll get to that in the next question. But for now, how much rocket fuel just to get it up there? What's changing anything? Look up, don't write this down. Why can't I just go like this? Oh, it would be nice if I could. So we have to go cosmic. Negative big G, big M, little m over R final minus negative big G, big M, little m over R initial. I do notice in the middle there on the next line I have a minus minus, which I'm going to turn into a plus on the next line. Okay. W equals negative. Kiefer, what is big G as a number exactly? Start over. Start over. Boy, did you defeat what I was hoping to say, but I'm going to try this. Do we all know that big G is 6.67 times 10 to the negative 11? Because it's on our formula sheet. It's a constant. I'm going to let you just write big G and not bother writing out the number. But on your calculator, you can write out the number. But it's less writing here. Kiefer, what's big M? More specific. Oh, by the way, if the question doesn't say a planet, assume Earth. If I'm on another planet, that I'll make sure I tell you. If I want you to be on the moon, it'll say around the moon. If I'm on planet Duick, it'll say planet Duick or whatever, and I'll give you the information you need. So assume Earth when in doubt. So big M is the mass of the Earth, which is what? Mr. Duick? What, Kiefer? Could I maybe just go capital M subscript E for mass of the Earth, and just know that on my calculator I'll type 5.98 times 10 to the 24th. It's on my formula sheet. Sure. On a test, I'd probably write the numbers out, but in your homework, if you want to cut corners, okay. Oh, by the way, do you notice how when we did the conservation of energy question, the little m canceled? Does the little m cancel here? No. Is there an m in work? Does it cancel here? In other words, should it take more rocket fuel to send the space shuttle up there than to send a small satellite up there? Yeah! Shouldn't cancel. I'm okay with that. What's little m as a number exactly? I'll do that. I'll put that number in. Our final is not 1.2 times 10 to the 7th. Can you all underline that word? What's another word for height that starts with the letter A and then that has an L? Okay, they've given me an altitude, and I need distance from the center of the planet. I need a radius. How can I convert that altitude to a radius? I heard this. I think you are going to add something, but I couldn't get the rest of it at all. How do I change an altitude to a radius? Anyone? I don't know. I'm asking. Yeah, here's what we're saying, folks, by the way, because some of you are looking like looking at your sheet. Look up. This should make sense. I've given you that. You need that. Better add the radius of the Earth. So I'm going to write 1.2 times 10 to the 7th plus, look up, lowercase r, capital E, radius of the Earth. Which is, we're going to try this again, Kiefer. What is the radius of the Earth exactly as a number since it's on my formula sheet? Good. Then there's a minus, which is a plus. And now, Dustin and Kedra, I want to show you what we did yesterday because we're being organized but lazy. Kedra, what letter is sitting right here? Capital letter. What letter is sitting right here? Capital letter. What letter is sitting right here? Capital letter. Capital letter. Lowercase. Lowercase. Are the tops identical? What we actually said yesterday is we're going to go ditto mark times ditto mark. Those are called ditto marks. Same thing is going to go there. You're going to, if you haven't seen those before, start using ditto marks. In university, in your freshman year, you will learn there's a shorthand for note-taking that university students have evolved, and you'll just pick up on it. You'll know that that's the abbreviation for therefore. You'll know that upside down, that's the abbreviation for the word because. Words that you're using all the time in your notes, you have abbreviations for. That's the abbreviation for which, W-H-I-C-H. Because there's a C there. There's all sorts of dumb abbreviations, and you'll kind of notice people next to you using them, and that's very, very clever. So ditto marks. Over, back to Kiefer. What's our initial? The surface of the? R-E. Pick your calculators up, but don't start typing yet. If you did, pause. Dustin and Kedra, here's what we decided yesterday. There is no way we want to type this in one step. Instead, we're going to go one expression at a time and write it down to about 5 sig figs, and you'll see why in just a second. So carefully type in negative 6.67 times 10 to the negative 11 times 5.98, scientific notation, 10 to the 24th, times 1200 divided by bracket 1.2 Scientific notation, 7 plus 6.38. Now, if you don't have your formula sheet in front of you to lift all these numbers from, you want your formula sheet in front of you to lift all these numbers from. And if you hit enter, you should get negative 2.60413, that, times 10 to the 10th. Mr. Dueck, yeah. Are we going to get a negative answer? Patience. By the way, we should get a positive answer because it should require us to add energy. We should have to add fuel. We should have to add a certain amount of work. So patience. Did you all get negative 2.60413 times 10 to the 10th? If you did not, now is your chance to raise your hand and I'll come look over your shoulder. Don't clear your calculator and I'll help you with it. Evan, you got it okay? Annika got it okay? Oh, okay. Annika, I was reading your body language totally wrong. So negative, I'm going to carry it. You know what? I'm going to write about 6 sig figs. That 0 after the 3 seems like a nice place to round off. So I'm going to go negative 2.60413 times 10 to the 10th plus. And then Kedra and Dustin, here's the weird, clever trick we said. Do you know how you already said the top is the same? I'm not going to retype this. I'm going to backspace so I can edit my last calculation. Probably you can go up arrow or left arrow or shift up arrow or shift left arrow. Or if you don't know how to bring back your previous line, later on I'll Google your calculator manual. We'll figure that out. Because it seems to me, by the way, for all of you, on my calculator, I want to delete the negative, which is at the very, very front. If I go up arrow twice, that puts me at the very beginning of my calculation without having to go left arrow, left arrow, left arrow, left arrow, left arrow, left arrow to get there. I'm going to delete the negative. And then on the bottom, I just want the radius of the Earth, so I'm going to delete the 1 and the point and the 2 and the times 10 to the and the 7 and the plus sign. And I think I now have the second term with less typing and less risk of a typo. So Dustin and Kedra and all of you, what we said last day is we're going to be really careful typing in the first term, making sure meticulously we get it right. And then we're just going to backspace and tweak it to get the second term. And if I hit enter on the second term, Dustin, you get 7.50, positive 7.50218. I'll round off after the 8 times 10 to the 10th. 7.50218. And now I'm going to add them together. The first term is negative 2.60413, scientific notation button 10, plus, haha, answer button. I'm not going to retype that. I'm going to carefully make sure I didn't make any typos. I don't think I did. And I get a positive answer. I was a little worried I was going to get a negative answer. I don't. I get a positive answer. I get 4.90 if I go to 3 sig figs now, times 10 to the 10th joules. If I now knew how many joules per liter I could get from rocket fuel, I could calculate how much rocket fuel I need. The only problem with that is when I added the rocket fuel, Ethan, that number would change. The 1200 would become bigger. So I would need to recalculate and I would need more rocket fuel. Oh, but the only problem with that is when I add the extra rocket fuel, little m would change. And so I would need to this is called the tyranny of the rocket equation. And it's once you figure out how much you need and then add the fuel that you need, you now need more than you thought that you need. So you add more fuel that you need, which now means you need to add more fuel that there's a way to get there in one step, but it's fairly complicated. The vast majority of the energy that we use to put stuff in orbit goes to fuel and the rocket structure itself. Because remember, if I need to add more fuel, I need to build a bigger tank, which means the rocket itself just got heavier because the tank just got bigger. So I need to add more fuel, which means I need to build a bigger tank, which means the rocket itself, not just the fuel itself made it heavier, but the rocket itself got heavier. Right now, for a standard rocket, about 1% of the rocket is payload. 99% of the rocket's mass is infrastructure, fuel, and structure, which is terrible. but it's what we got. Of course, since this satellite has no KE, it will simply fall back to the Earth because there is gravity still up there. So to lift an object, we only need to give it potential energy. But to put it in a stable orbit, did I say orbit? Gravity is what's pulling me in a circle. We need to give it both potential and kinetic energy. Kinda, sorta, kinda like example 2. 3. I like example 2. 3. I like example 2. 3. I like example 3. It's a nice question. Kedra, what's example 3 asking me to find? How much what? Okay. Can I go MGH? No. Can I go force times distance? No. So I'm going to jump straight to work equals the change in potential plus the change in kinetic. But now, since we're being put into a stable orbit, I'm sorry, but the change in kinetic is not 0. There's going to be some kinetic energy. Yeah, I saw Alex. Oh. Alex, I'm not going to do this in one step. I'm going to find the change in potential, get an answer, and I'm going to find the change in kinetic, get an answer, and then I'll add them up. Alex, which one do you want to find first? Change in potential or change in kinetic? Doesn't matter, I don't care. Pick. Change in potential? So, change in potential equals, what's change in anything? Pause. Is that going to be MGH final minus MGH initial? Cosmic. So you ready? Negative big G, big M, little m over R final minus negative big G, big M, little m over R initial. Mr. Dewitt, there's an M in everything. Doesn't it cancel out? Kiefer, does that little m cancel out? No. Which, again, should make sense. Of course it should take more fuel to put something bigger up there. Keeping it up there, done the math. They'll all be at the same speed at that altitude. Okay. Negative. Alex, do you know what big G is as a number exactly? I'm going to put that there. Big M, mass, Earth. Little m, 925. Fine. James, what's a minus? Minus the same as? Yeah. You going to make it? Because you're looking a little tired. Okay. Your blinks were getting longer and longer there. Oh. Are the tops the same? The same times the same times the same. What's our initial? Where are we starting out? Surface of the? So what's our initial radius? Radius of the? Oh, what's our final? You were wondering because I kind of skipped ahead there in my eagerness. What is our final? Is it 2.6 times 10 to the 7th, or do I need to add the radius of the Earth to that one? That 2.6 times 10 to the 7th, is that a radius or an altitude? Read the question. Oh, so I'm just going to put that as is. No need to add the plus 6.3. They already did that for me. All right, humans, it's calculator time. Negative. Hey. If you know how to bring back several lines, like I can't help noticing that this line has a negative, a big G. I can just delete from right about here. But I already got part of it typed. Now, if you don't know how to bring back several lines, your calculator might not allow you. Many will, though. Read the manual. 925 divided by 2.6, scientific notation button 7. Abby, did you get negative 1.419? You know what? That 0 is probably a good place to round off since it's a 0. Negative 1.419 times 10 to the 10. Yes? No? Yeah? Oh, she's still typing. Am I right? I could be wrong. Yeah? When do you have to leave, Thomas? Okay. It's going to be close, but we'll be close. Negative 1.41, what did I say? 9? 0 times 10 to the 10th plus backspace, delete the negative. And then on the bottom, instead of 2.6 times 10 to the 7th, 6.38 times 10 to the 6th. Positive 5.7829. 5.7829 times 10 to the 10th. Negative 1.419 times 10 to the 10th plus answer button. And I get 4.3639 times 10 to the 10th. Is that right, folks? People nodding? That's joules. Put a box around it because we're going to need it later. You're going to find if you're figuring out how much energy to lift something to the correct orbital radius, it's almost always going to be 10 to the 10th or once in a while 10 to the 11th. Steph, if I go really high. We're not done. That's the change in potential. What else do I need to find? The change in? What's change in anything? So this is going to be a half m v final squared minus a half m v initial squared. You know what? Where it says v final, if you want to, you can scratch out the f and put an orb right there. It's going to be the orbital speed because we are in orbit. Are any of these 0? Well, our orbital speed can't be, so v final cannot be. Are we starting at rest? Is v initial 0? When the rocket's sitting on the pad, how fast is it traveling? It depends how fussy you want to be. Technically, and I'm being just accurate, in real life right now, are any of you at rest? Why? Earth spinning, and we use that kinetic energy for our VI. What part of the Earth spins the fastest? Along what? The equator. Where would be the best place to launch rockets from? That's what Elon Musk is trying to do. He wants to launch from ships along the equator. In the northern hemisphere, the further south you can launch, the more of that KE VI initial boost you'll get. Where does NASA launch from? As far south as possible in the US. Conveniently also going directly over an ocean so that if they have to abort and blow the craft up, everything will land in the Atlantic Ocean. One of Atlantic Ocean's nicknames, it's the graveyard for aborted space missions. There's plenty down there because stuff does go wrong. Even if it's radioactive, you know what? As long as it sinks to the bottom of the Atlantic, we're probably okay. That's why Russia had such a tough time with their space program. When you think Russia, do you think, oh, sunny southern climes near the equator? No. So even today, Russia's rockets are workhorses. They are beasts because they had to engineer them that way because they were launching from so far north. So is VI 0? Technically no, but Kiefer, would I like VI to be 0? Where are we launching from if VI is 0? Superman's Fortress of Solitude or Santa Claus's Workshop. I don't care which one you're going with, but one of them is developing a missile rocket program. So we can say this, and we're assuming we're launching from Santa Claus's Workshop or Superman's Fortress of Solitude. There's room up there, and they'd probably get along in a weird way. Okay? This is the second longest question we'll do all year. Did they give me Alex V. Orb?
Yes.
The longest question that we'll do all year, and you're going to do one in the homework, would be if instead of giving you V orb, I just gave you the radius, and then you said, well, gravity is what's pulling me in a circle, and calculated V orb. I actually did that. That number, you'll notice I gave it to you like 4 sig figs or something, because I wanted to give you what speed it would actually have to travel at this particular radius. So I ran that for you, but that's how I got that 3,917. In fact, you can make a little note if you want to. This is going to be V orb was, what was it? Square root of big G, big M over R orb, I think is what when we did gravity is what's pulling us in a circle and cross multiplied. I think that's what we ended up with. That's what I did. For now, we don't have to do that. It's going to be a half. Which M? Mass of the Earth or mass of the satellite? 925. V was 3,917 squared. What's the change in kinetic energy? Do you get 7096? Oh, do you get that? That's 7.096 times 10 to the what? 9 is correct. You're going to find generally the potential energy is in the 10 to the 10th or 10 to the 11th range. The kinetic energy will be in the 10 to the 9th range. Most energy, much bigger portion of the energy, roughly 10 times more energy, is used to get it to the correct altitude. Only 1/10 of the energy is used to keep it in orbit. 7.096 times 10 to the 9th. Well, we're not done. Because we weren't trying to find the change in potential. Neither were we trying to find the change in kinetic. Kedra, what were the first 3 words? We're trying to find the work. How do I find the work? It's the change in potential plus the change in kinetic. So, work is going to be change in potential 4.3639 times 10 to the 10th plus 7.069 times 10 to the 9th. Thank God I can use my answer button for that second one. Also, by the way, if your calculator has the ability to store values and then retrieve them, it's really handy for this stuff. Read your manual. Can calculators do that, Mr. Dewick? Yes, they can. Do you get 5.07 times 10 to the 10th? Yes. Units, work, joules. That's how much energy the rocket fuel would have to supply to put that satellite in orbit. By the way, we've ignored the mass of the actual spacecraft. That's just the mass of the satellite. So this is why right now it costs about $100,000 a pound to put something into low Earth orbit. It's just expensive. Made worse by the fact that until SpaceX came along, all of our rockets were used once and get destroyed, except for the space shuttle. The space shuttle was built. You can go ahead, Thomas. Oh, you just want to know the homework? Thomas, I can give you the homework right now before you go. Here's what I assigned last class. Unfortunately, a fair chunk. Can you all, if you want to, circle number 1, number 3, number 7. Number 1 is just wants you to find the orbital PE. Really, it's the cosmic potential energy. Number 1, you're just going to go negative big G, big M to over R. Number 3, it wants the final PE and then the work. So you'll go work equals change in potential. I think plus change in kinetic, except change in kinetic is 0. Number 7, it's not asking how much work. Instead, I think it's a change in height, change in speed, yucky, curvy path, conservation of energy. Number 9. Number 10. How far are we going out in question number 9? An infinite distance? What's my final potential energy then if I'm out at infinity? It sounds way tougher, but actually if I end up at infinity, that one's going to be a 0. Or if I start at infinity, my initial would be a 0, which, although it makes the question sound tougher, actually, no, the math is way easier. 10 is good. 11 is good. 13 is good. 14. 15. The rest of us will keep going for a little bit longer, and then I'll turn you loose. Example 4. A missile is launched from the surface of the Earth. So here's a thought puzzle, but Evan, we're going to simplify it as much as possible. We're going to ignore air resistance, would that we could. And let's say that its fuel is used all at once, so it hits its maximum speed and then coasts the rest of the way. As it rises, what happens to the kinetic energy? And what happens to the orbital or cosmic potential energy? Since this is a 2-column question, let's do this column vertically. First of all, as it rises, what happens to its speed if we're coasting? Is it going to speed up, slow down, or stay the same? When we launch things away from the Earth, they just speed up on their own? I think you've got a warped sense of physics. Please be obvious. You're telling me that as we launch objects from the Earth, we give them a kick and they speed up and they rush off into the sky on their own. Dustin, I got to go. Boy, clearly there's some weak links in that chain. Dustin, what? So it slows down. So what happens to its kinetic energy? Yep. So I'm going to go like this. No, no, yes, yes. In fact, I'm going to cross out A and B right now because they can't be right. What happens to its orbital or cosmic potential energy then? Increases or decreases? Pardon me? Yeah. Why? The energy's got to go somewhere. We're losing kinetic and we're turning it into the kinetic is at the height. Okay. So yes, no, yes, no. Redeem yourself, Evan. What's the correct answer? Thank you. Turn the page. I would love to do example 4, 5. But I'm sensing as Kiefer yawns that you're tired, so I'm just going to get you. I'm giving you a lot of homework, and I don't like giving homework over extra long weekends, normal weekend, whatever. So, first of all, what's A asking you to find? Kedra, loud and proud. Did you say orbit? I can say gravity is what's pulling me in a circle, and I will have to, and I'll get the R by itself. They gave me a V, so it would be equals mv squared over R. I would get the R by itself. It's doable. Then, what's B asking me to find, Kedra? How much? And now it's exactly the same as all of this, because I gave you the speed, you calculated the orbital radius, and it would be repeated this question.